Hey everyone, and welcome. Today, we're diving deep into the specialized hardware that serves as the actual brain for modern AI. We're talking about the custom-built chips that took artificial intelligence from a cool idea in a lab and turned it into the powerhouse technology that's literally shaping our world. All right, let's get into it.
So let's start with the big question, right? Why does AI even need its own special brain? I mean, why couldn't we just use the super powerful processors we already had in our computers? Well, the answer comes down to a massive, and I mean massive, computational bottleneck that almost stopped AI progress dead in its tracks. And you can boil that whole problem down to just two words: insatiable hunger. As AI models got smarter and more capable, their appetite for data and raw computing power just grew exponentially. This wasn't a small step up, it was an absolute explosion.
To give you a sense of what that hunger looks like, get a load of this number: 540 billion. That's how many parameters are in Google's advanced language model, PaLM. You can think of parameters as these tiny digital knobs or connection points, and every single one of them has to be calculated and fine-tuned, which requires a truly mind-boggling amount of math.
And this, well, it created a huge crisis. Trying to train a model with billions of parameters on the hardware we had was becoming completely unsustainable. We're talking about training runs that could take weeks, months, even years, just burning through unbelievable amounts of energy and money. AI was basically hitting a brick wall.
So to really understand the solution, we first have to look at the old guard of processors. It was a showdown between the chips that were already powering everything, from our laptops to our gaming rigs, the CPU and the GPU. The problem, you see, was baked right into the chips themselves. On one side, you've got the CPU, the Central Processing Unit. It's your classic jack-of-all-trades, a versatile workhorse, but it really struggles with the kind of massive parallel data crunching that AI needs. Then you have the GPU, the Graphics Processing Unit. Now, this was a huge leap forward because it was designed for graphics, which meant it was awesome at doing thousands of simple things all at once. But it still wasn't tailor-made for the very specific type of math that neural networks depend on. It was clear a new contender had to enter the ring.
And when you visualize the difference in speed, it is just staggering. What might take a CPU a whole month to train, a GPU could knock out in a week. That's a fantastic improvement. But what if you could do it in a single day? That's the kind of game-changing leap that was needed, and it called for an entirely new kind of processor, one built from the ground up just for AI. And that, my friends, is where the hero of our story comes in, the TPU. So what is its secret sauce? What makes this little chip so uniquely powerful that it can just leave other processors in the dust when it comes to artificial intelligence?
A TPU, or Tensor Processing Unit, is what we call a domain-specific processor. So unlike a CPU or a GPU, which have to be good at a lot of different things, Google designed the TPU to do one thing and one thing only: accelerate the very specific math that's at the heart of machine learning. It's a specialist, a master of one trade, not a generalist.
And right at the core of the TPU is something called the Matrix Multiply Unit, or MXU. If the TPU is the brain, you've got to think of the MXU as its beating heart. This piece of hardware is laser-focused on performing matrix multiplication, which just happens to be the single most common and demanding calculation in any neural network. It was literally built for AI math.
So how does it get this incredible speed advantage? Well, it all comes down to a really clever three-step process. First, the TPU uses special memory to load massive blocks of data straight into that MXU. Second, the MXU itself is basically a huge grid of thousands of tiny calculators that perform all their multiplications and additions at the exact same time in a single tick of the clock. And third, it uses a specialized number format called bfloat16, which is good enough for AI accuracy, but allows for way faster and more efficient math.
Okay, so that's the how, the tech behind the magic. But what about the so what? All this incredible speed and efficiency isn't just an engineering flex. It has enabled breakthroughs that are fundamentally changing the world around us. And things moved so fast. I mean, back in 2015, the very first TPU was already supercharging Google search. By 2018, the third version, which was so powerful it needed liquid cooling, was training the revolutionary BERT language model. And by 2021, the fourth generation was delivering exaflop scale power, paving the way for mind-blowing scientific breakthroughs like AlphaFold, which predicted the structure of nearly every protein known to science.
And the impact is literally everywhere you look. This same core technology is what's at work when a self-driving car spots a pedestrian, or when Google Translate gives you an instant translation, or even when your YouTube feed seems to read your mind. It's being used to speed up drug discovery and even help doctors spot cancer earlier in medical scans. The key takeaway is this isn't some abstract tech in a data center. It's having a real, tangible impact on our lives. All this rapid progress, of course, leads us to wonder what's next. What are the big challenges and the even bigger questions waiting for us on the horizon when it comes to the hardware that powers AI? And really, it all comes down to this central tension, this push and pull that's shaping the future of AI. On one side, you have AI models that just keep getting exponentially more complex, demanding more and more and more power. But on the other side, that insatiable hunger has a very real-world cost, creating an urgent need for more sustainable, energy-efficient ways of computing. The race for more power has become a race for more efficiency, too. Which leaves us with one final big question to think about. We've seen how a specialized brain like the TPU completely unlocked the last decade of AI progress. But as AI continues to evolve and get even crazier, is one type of chip going to continue to rule them all? Or, for the next generation of challenges, are we going to need a whole team of different, even more specialized brains all working together?